So the second way to find the limit of a function is to find its limit algebraically. And so when we're doing that, you can consider three important points. Number one is you can ask yourself, is the value that x is approaching part of the domain? Meaning that can the x value simply be substituted into the function? In other words, can we ever just plug a number in to find the limit? And the answer is yes. When the value that the limit is approaching is part of the domain of the function, you just evaluate that function at the value. So, for example, in example 1 here, you have the function x plus the square root of x. Well, 4 can be plugged into this without it being a problem. 4 is in the domain. So if you just plug 4 in, you get 4 plus the square root of 4, which is 4 plus 2, which is 6. So the limit of this function as x approaches 4 is 6. Second thing you can think about is if the function is rational. In other words, if the function is like this first example here that we did graphically, this is a rational function. If you can factor this, x squared minus 1 factored into x minus 1, x plus 1, and then you can cancel these, then you get x plus 1. Now 1 is in this domain, then you can put 1 in. So if the function is rational and you want to find the limit algebraically, you can factor and then reduce the function and then plug in the value that x is approaching, because we're finding the limit. We're not evaluating the function, we're just finding the limit. And the third point is the value that x is approaching either positive or negative infinity? And we have a bunch of rules for this that we'll go over. So number one, sometimes you can just plug the number in. Number two, if it's rational, you can factor and then cancel and then plug the number in. And number three, if the function's approaching positive or negative infinity, and we will talk about ways to think through those. Here are some finding the limit algebraically examples. I've already talked about this one, but what you want to do when you're finding the limit is, if you look at this function x plus the square root of x, think about the domain. This domain is good for all values of x that are greater than or equal to 0. There's a restriction on the square root. So as long as x is greater than or equal to 0, it's in the domain. So if we want to find the limit of this function as x approaches 4, 4 is in the domain. So all you have to do is plug 4 in, and you get 4 plus the square root of 4, which is 4 plus 2, which is 6. So I've got an extra example here since we've already done that one. The limit of the function x squared plus 3x minus 5 as x approaches 2, this is a parabola. There are no restrictions on the domain. The domain here is all real numbers. So 2 is in the domain. So that means all you have to do is plug 2 in. So if you plug 2 in, you get 2 squared plus 3 times 2 minus 5. So the limit as x approaches 2 of 4 plus 6 minus 5 is 10 minus 5, which is 5. Okay, well, what if you have an example like example 2? The limit of the function x squared plus 6x plus 8 over x plus 4 as x approaches negative 4. This is a rational function, and notice that there is a restriction on the domain. X cannot equal negative 4. Well, you're trying to find the limit as x approaches negative 4, so you can't just plug it in. But you can factor that numerator. So the limit as x approaches negative 4, x squared plus 6x plus 8 factors into x plus 4 and x plus 2 over x plus 4. Notice how I'm writing perfect limit notation every time. The limit as x approaches negative 4, these x plus 4's cancel, and you have x plus 2. So the limit of x plus 2 as x approaches negative 4, now you can plug it in. Negative 4 plus 2 is negative 2. So if you evaluate at -4, that value does not exist. But if you want to find the limit as x approaches -4, it's -2. So for a rational function, you factor and try to cancel. And then you can evaluate. Okay, the last example is a piecewise function. And a piecewise function, this piecewise function looks like a line, -x plus 6 when x is less than -1. And it looks like a parabola when x is greater than or equal to -1. So the domain has been split at x equals -1. And we want to find the limit of this function as x approaches -1 from the left and from the right, because if they are the same, then the limit exists, and if they are not the same, the limit does not exist. So since we have a line here, a parabola here, split domain at -1, what you want to do for a piecewise function is you actually do want to find the limit as x approaches -1 from the left of this function. I'm just going to call it the function, so I don't have to rewrite all that. Well, the -1 from the left, x is less than -1, that's to the left. So you would simply plug -1 into this top function. So -1 plus 6, so the limit as x approaches -1 from the left of 1 plus 6 would be 7. If I plug -1 in here, I get 7. The limit as x approaches -1 from the right of the function, that's going to be, if I plug -1 in here, the second one, because from the right where x is greater than or equal to -1, those are numbers to the right, so I'm plugging into the second one, so that's -1 squared minus 2 times -1. So the limit as x approaches -1 from the right would be -1 squared is 1, -2 times -1 is 2, so that's 3. So the limit as x approaches -1 from the left is 7, and the limit of the function as x approaches -1 from the right is 3. Therefore, the limit as x approaches -1 of this function does not exist. Here are some more examples for finding limits algebraically off of a PDF file I found on the internet. The first one is number 2. The limit of this function as x approaches 1. Well, this function is undefined when x is 2/3. So 1 is in this domain. So even though this is a rational function, 1 is in the domain of this rational function, so all I have to do is plug 1 in. So 2 times 1 plus 1 over 3 times 1 minus 2. So the limit as x approaches 1 of 3 over 1 is 3. However, this one, the limit of this function as x approaches 2, 2 is not defined. So this rational function, we're going to want to factor it. And this factors into x minus 2 times x plus 1 in the numerator over x minus 2. Then we can cancel these factors. So the limit as x approaches 2 of x plus 1 is equal to 2 plus 1 is 3. Okay, the next example I picked is number 6 from that worksheet. The limit of the function as x approaches 4. Well, 4 is not defined. It's not in the domain. And you can't factor this numerator. And so things will not cancel. Well, here's a little trick that I happen to know. That is, when I see a square root minus some real number, a lot of times it'll work to multiply by the conjugate of that. And the square root of x minus 2 has a conjugate, and it is the square root of x plus 2. Now I can't just multiply by the square root of x plus 2. What I'm going to have to do is multiply by a convenient form of 1. So I'm going to multiply the numerator and the denominator by the square root of x plus 2. How did I know to do that? I just done enough where if I see something like this, I just try multiplying by the conjugate, and remember the algebraic rule of multiplying by 1. So this is going to give me the limit as x approaches 4. The square root of x times the square root of x is x. The outer and inner terms will cancel. That's what happens when you multiply by conjugates. And negative 2 times 2 is negative 4. And in the denominator, I don't want to FOIL that out. I'm going to leave it in factored form because I see what I have here. I end up with an x minus 4 in the numerator, and I have an x minus 4 in the denominator. So I can cancel that out. So the limit as x approaches 4 of, there's an understood 1 that pops up in the numerator, the square root of x plus 2. Now 4 is in that domain. So this is the limit as x approaches 4 of 1 over the square root of 4 plus 2. I just plug it in. And so that is 1 over 2 plus 2. That's 1/4. Okay, the last example on this page, the limit of this function as h approaches 0. Now you may not know this now, but this is actually part of the difference quotient that you may have calculated a lot in Math 171. And this h stands for the distance between the two x coordinates that I referred to in the PowerPoint. If I let the distance between the two x coordinates go to 0, I can find the limit of the average rate of change as the distance between the two x coordinates goes to 0. So here's the math for that. What we want to do is, just like you did when you were finding the difference quotient in Math 171, you want to multiply this out. I like to do square double square, so that would be 3 squared is 9. 3 times h is 3h, but there's 2 of them. So if you double 3h, you get 6h. H squared is next. And then minus 3 squared would be minus 9 over h. So the limit as h approaches 0, 9 minus 9 is 0. So you have 6h plus h squared over h. This h divides into both of those terms. So that's 6h divided by h is 6, and h squared divided by h is h. Well, now I can put 0 in for h, and so the limit is 6. Alright, so the last example is a piecewise function, and says that the function is behaving like x plus 1 when x is less than 2. It's behaving like parabola, x squared minus 2 when x is between 2 and 4. It's behaving like a square root function, x squared to x plus 5 when x is greater than or equal to 4. Okay, so again, for limits, if I asked you this question, find the limit of the function as x approaches 2, you would have to find the limit as x approaches 2 from the right and as x approaches 2 from the left. So this is question 17. The limit of f of x as x approaches 2 from the right. Well, x is greater than 2. When x is greater than 2, that's the numbers to the right of 2, then you would use the parabola. So if I put 2 in here, 2 squared is 4 minus 2 is 2. So the limit of this function as x approaches 2 from the right is 2. The limit of the function as x approaches 2 from the left, those are numbers that are less than 2. The numbers to the left of 2 are less than 2. So I would use this function. So putting 2 in here, I get 3. Now I can answer question 19. The limit of the function as x approaches 2 does not exist because from the left it was 3 and from the right is approaching 2. Okay, the last question 20 means to evaluate when x is 2. Now I toyed around with the idea, is this a typo? Because on the PDF file problem I found, there is a actual hole at 2 because x never equals 2. X is less than 2 and x is greater than 2, but never x is never equal to 2. So I toyed around with putting an equal to here, thinking maybe it was a typo. Then I decided against it because, these things can happen. So when x is 2, the function is actually undefined. There is no value. Now, let's say it did have an equal to here. Then you would use this function, this piece of the function, to evaluate 2, and you would get 2. But as it's written, there is no value when x is 2. Here are 3 rules for working with infinity. So when a function or decimal base is raised to a power that is a variable, and the variable is approaching infinity, the limit is 0. That's the rule number 1. Let me explain. So here is the base, 0.979, and 0.979 is less than 1. So this is a fraction that's less than 1. And we are raising this fraction less than 1 to infinity because we want x to approach infinity. So if you have a number that's less than 1 and you're raising it to a power, the denominator is going to get bigger than the numerator faster. So this function is going to eventually head to 0 since x is approaching infinity. Similarly, this is the limit of 1.5 to the negative x as x approaches infinity. You have to remember a little bit of algebra here. 1.5 is 3 over 2. So this time, this number is greater than 1, but it's being raised to the negative x power. So remember, a negative exponent flips the fraction. So 3 over 2 to the negative x is the same as 2 over 3 to the x. So 2 over 3 is less than 1. So if you raise a number, a fraction that's less than 1 to infinity, it's going to eventually head to 0 because the denominator is going to get bigger than the numerator. Eventually, it's going to go to 0. Here's rule number 2. When a variable is in the denominator of a fraction and it is approaching infinity, the limit is 0. So we have a constant 5 over x minus 6, and we want to find the limit of 5 over x minus 6 as x approaches infinity. Well, 5 stays 5, but x is going to go all the way to infinity. It's going to become a very large number eventually. So 5 divided by a large number minus 6 doesn't matter if you've got infinity minus 6. So 5 over a large number, the denominator is huge, is going to go to 0. So the limit is 5 over x minus 6 as x approaches infinity is 0. All right, rule number 3, you might recognize from Math 171. When working with a rational function, all terms except the leading terms, as long as we have the functions in descending order, in the numerator and denominator can be eliminated, and then you evaluate the expression remaining. So the limit of this rational function as x approaches infinity, this leading term here, 5x squared, and this leading term here, 2x squared, are all that matters. So, and then x squared divided by x squared, they cancel out to 1. So the limit of this function as x approaches infinity is just these leading coefficients, 5 over 2. Okay, sometimes finding limits algebraically, you sort of just have to think through. And the first thing, sometimes when you find limits, you'll get an indeterminate form. You'll get 0 divided by 0 or infinity divided by infinity. Now, if you get 0 divided by 0, it's important to know that that is not 0. That's just, you can't tell. And so you would need more calculus to calculate a limit if you got something like 0 over 0 or infinity over infinity. However, there are some determinate forms that you can find, and the first one I wanted to look at is the limit of 60 divided by 2x squared as x approaches 0. So you can't put 0 in here because you get an undefined value. And so what you have to do is you have to find this limit as x approaches 0 from the left, and it's going to be hard for me to write anything down because I'm really sort of thinking through this. So think about numbers to the left of 0. Those are negative numbers, and they're really, really, really small. So if you put a really, really, really small negative number in here, let's think about the negative part. If you square a negative number, what happens? It becomes positive. So if you put a really, really small negative number in here, it becomes a really, 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 really small positive number. If I multiply that by 2, I still have a really, really small positive number. So what I end up with is what I have written over here. I have some constant k divided by a small number. For example, 6 divided by 0.000001 is 6, 1, 2, 3, 4, 5, I think 6 billion or 6 million, not sure, but large. So a constant number divided by a tiny number is going to give you a very big number. Okay? So you got to remember that. K divided by small is big. And so remember how we said this is positive because this negative number squared is positive. So 60 divided by a really large positive, a really small positive number is a really big positive number. In other words, the limit of this function as x gets really close to 0 from the left is heading towards infinity. Alright, if you look at the limit as x approaches 0 from the right, then the same exact thing is going to happen. If you put a really, 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 really small number that's positive and square it, you get a really small positive number times 2. You get 60 over a small positive, and that's going to give you a big positive, and that's going to go to infinity. Positive infinity. So they both head towards positive infinity. The limit does not exist. Okay? That is not a limit. However, it is a limit that does not exist that we can describe as it's heading towards positive infinity. So that's what we write down. Okay, so the second one, it's the limit of this function as x approaches negative 1. Negative 1 is not in this domain, and you can't plug negative 1 in. So again, what we'll do is we're going to look at the limit of the function as x approaches negative 1 from the left. And so if you put negative numbers that are to the left of negative 1 in the numerator, you're going to get 2 times some negative number, which is a negative, minus 6, which is a negative. So we're going to have some negative number in the numerator, over, if you put negative 1 and you get really, really, really close to negative 1 on the left, I just pick a number like negative 1.01. Negative 1.01 plus 1 is, since this number is larger than the positive one, it's a really, really small negative number. So what we have is a negative constant over a negative small, and a negative divided by negative is a positive. So a constant divided by small again is a big. A negative divided by negative is a positive. So as we approach negative 1 from the left, you head towards positive infinity. Okay, now we need to do the same thing, negative 1 from the right. If I put a negative 1 number close to negative 1 approaching from the right, I'm going to get, like if I put in 0, I get a negative. If I put in negative 0.9, I get a negative. So again, I'm going to get a negative number here. And then if I put a negative number negative 1, close to negative 1, but from approaching from the right, I'll put in negative 0.99. And that's going to give me a really teeny tiny small positive number this time, because negative 0.99 is smaller than positive 1. So negative 0.99 plus 1 gives you a small positive. Okay, so a negative divided by a positive is a negative, and a constant divided by a small is a big. So this time this is approaching negative infinity. Okay, so the limit of this function as x approaches negative 1 from the left is positive infinity, but from the right it's negative infinity. So not only does this limit not exist, you can't even describe it in any way. It's not heading towards one direction or the other, so it just does not exist. Okay, all right, the other ones have to do with infinity. So the limit of this function is a nice continuous line as x approaches negative infinity. Well, 3 times a large negative number is negative minus 5. So this limit does not exist. This line is going to keep on going forever and ever and ever. Does not exist, does not have a limit, but we can describe that as it's heading towards negative infinity. Okay, this one, the limit of 2x over 60 as x approaches positive infinity. So if I put a large number here, 2 times positive infinity is going to go to positive infinity. Positive infinity divided by a small number 60 is still going to head to positive infinity. Again, this limit does not exist. This is just a nice linear equation that goes on forever and ever. The limit doesn't exist, but we can describe the limit. It's heading towards positive infinity. Couple more. Again, the limit as x approaches negative infinity. This time we've got the x in the denominator, so we have, again, we have a constant k over 2 times negative infinity is a very large negative number. And any time you have some constant divided by a large number, it's going to head to 0. So this limit, as we head towards negative infinity, it heads towards 0. So it exists. You can think about your rules that you learned in Math 171. If you have degree 0 over degree 1, if you have small degree over large degree, the limit it is going to head towards 0. The horizontal asymptote would be y equals 0. And that's what you were doing. You were finding limits back then. Okay, here the degree 1 over degree 1, remember what you can do is just look at the leading coefficients. So as x approaches infinity, they're going to get very large at the same rate. So all you have to do if you have the same degree is look at the leading coefficients. So this limit is 30. And the last one, limit of 60 over e to the x minus 1 as x approaches negative infinity. Got a little work to do here. So if I plug in negative infinity here, that you can use negative exponents. Remember, a negative exponent isn't a negative number. That just flips it. So e to the negative infinity is the same as 1 over e to the positive infinity. And 1 over a very large number, e to the infinity, to infinity is a large number, goes to 0. So we have 60 divided by 0 minus 1. Well, 0 minus 1 is negative 1. And 60 divided by negative 1 is negative 60. So there is a way to find a lot of limits, or at least describe limits that don't exist, whether they're going to positive or negative infinity, without using Excel. You could use Excel for all of these. You could put in very small numbers that head towards negative infinity, which would be numbers whose absolute value is very large. It's just they have a negative in front of it. You could put in large values to represent positive infinity. and create a table of values, and you could find those answers that way. But there is a way to do this algebraically.